Hello and welcome to our lecture on mesh versus nodal analysis. We've learned both of the circuit techniques, and now we're going to investigate a couple of different things about the comparison for both of those. So I just wanted to start by mentioning that I have a special guest with me here today. And so Bing the dog is here helping us out. He tends to prefer mesh analysis, but it depends on the situation. In any case, one of the things that we wanted to take a look at is with both mesh and nodal analysis, we either get a set of currents or, in the case of nodal analysis, we get a set of voltages. But that might not be the end of the story. So imagine that we had this circuit and we solved it with mesh analysis. We're going to get the list of the currents for each of the meshes. But the problem might be asking us what the voltage across a particular component is, or what the current between two nodes would be. So if we had to solve for V6 and for I9, and we did go through the analysis of mesh or nodal, we still might have some work to do. But I wanted to emphasize, once we get those characteristic currents or voltages, then solving for other currents and voltages across components is easy. So for example here, let's talk about V6. Now assume we've solved with mesh analysis, and we want to find V6, and we have the value for I2. So the current going through this resistor is I2, and I2 is going around clockwise, and so it's entering the positive node. So for this, V6 is just I2 times 6 ohms. And when we multiply that out for I2, it's 150 milliamps. And for that, we would get 900.6 millivolts. Now let's say that we wanted to find the current I9. Well, I9 would have been used when we did mesh analysis. What was the current I9? Well, I9 goes from left to right, and so it's going to be I3 minus I2. So I3 minus I2 is going to be I9. I9 is going to be I3 minus I2, which is going to be equal to 0.157 minus 0.1501, and that's going to be equal to 0.0069 amps, and we'll write that in engineering notation as 6.9 milliamps. So 6.9 milliamps. Now realize these two values are pretty close, so we needed an extra sig fig in here, or else we're going to lose our precision. Normally we just go with 3 sig figs, but when we're subtracting values that are close, then we'll see that those sig figs start to drop out when we take the difference of them. So here's our two answers. And if a problem asks us for voltages or currents through individual components, well, as long as we have the characteristic currents for mesh, then it's not too bad to find the individual values. So we've got the exact same circuit here, and let's say that we went through the trouble of solving for the nodal voltages. So we run the nodal process on here, and we get the two voltages V1 and V2. And again, we're asked the same thing, determine V6 and I9. Well, let's talk about V6. V6. When we look at this, we didn't solve for this thing at the top is actually a node, but we see that there's 2 volts. And so we didn't have to solve anything. We know that this is 2 volts up at the top. So all we need to do is take the difference between the 2 voltages, 2 volts and V2, in order to find V6, and it doesn't involve any currents at all, just a difference. And which one do it? Well, we are going from plus down to minus, so this is going to be the plus, and we're going to subtract off V2 as if we're going downhill. We want to know how much we go downhill across V6. So V6 is going to be 2 minus whatever V2 is, and that's going to be 2 minus 1.099, and that's going to be equal to 0.901 volts, which is equal to 901 millivolts. And again, here we had that extra sig fig to help us down at the end here. And so 901 millivolts. And what did we get? Up here we got 900.6 millivolts. And within the precision that we're measuring things, or that we're reporting these values, and those answers match to within that precision. Now let's take a look at I9. Well, we actually used the current I9 when we were writing the KCL equations. So when we wanted to know what the current running out of node 1 was, assuming we were using nodal, the current going out, what did we do? We said V1 minus V2 divided by 9 represented that current. So V1 minus V2 over 9 represents this current I9. And when we do that, we get 1.161 minus 1.099. We'll divide that by 9, and we get a pretty small number, 0.00689. That's why we had these 4 sig figs in here, because we were taking a difference. And that's going to be equal to, that's amps. So we'll put it in engineering notation. We get 6.89 milliamps. And again, we look back to the top. We got 6.9, we got 6.89 to within our precision, then those agree. So the whole purpose of this is to say, even if you do solve nodal or mesh and you get those characteristic voltages or currents, you still may have a little bit of work to do in order to find the voltages across independent values of components. But once you get all of the voltages, then it's relatively easy to solve for those. Next, let's look at an analysis of a particular circuit. When we're solving this, we can solve it either way, but we probably want to solve it the easiest way. Why? Well, it takes us less time, but also because it's less prone to errors if we have to do a fewer number of steps. So the first thing that we could say is, okay, I'm approaching this. Let's say that I want to do mesh analysis. How many meshes? Well, we move these through. And so we would have 3 different meshes. How many meshes? 3. Which means we would have 3 equations and 3 unknowns. Next, we say how many nodes are in the circuit. Well, when we look at it, we'd say, okay, here's a node. And say, here's a node. There's definitely those 2 nodes. Now, this is technically a node as well, but it's not an interesting one. It just connects 2 different components. So although this technically fits the definition of a node, we wouldn't call it one because we know what the voltage is here already. It's 1 volt. All right, so we're all ready to put down 2 here, but you know what? We've missed another one because this is a node here, but the first step is always to pick your reference node. And so we would be grounding that out. So that's the 0 node. It wouldn't come into play. Well, it depends on how you count them then, but the idea is we'd want to know how many equations there would be. So here there'd be 2 equations worth of nodes in that, but technically there's 4. This is the answer we'd be looking for, the answer that we'd be caring about, because we want to know how many equations there would be. So which would be the best? All right, well, you know, the end of the story is 3 equations, 2 equations. Yeah, probably you'd rather choose the 2, but there's an added bonus for nodal analysis in this particular case, because if we look here and we say, okay, I'm going to write the equations for, wait a minute. If I choose this to be V1, I already know what my voltage is. V1 is going to be just 1 volt. So then, how many equations would I have? Just 1. And so in this case, we would almost definitely like to use nodal, because not only is nodal fewer equations, one of the equations just drops out. So with this, we'd have one equation, one unknown, and so we're going to put an exclamation point after that. Next, we're going to solve a circuit in two different ways. So we have this circuit, which is similar to the one above, a little bit of differences. We take a look at this, and we need to solve for I-12. Well, we could try to solve for I-12 directly. Nope. What we'll do is we'll pick either mesh or nodal. In this case, we'll do both. And then once we get all the voltages or all the currents, then we can solve for I-12 after the day is done. So don't worry about the fact that I-12 is being asked for and it's across an individual component. Now just solve the whole thing each way. So let's do nodal analysis. So we might say, oh, nodal seems good for here because we have three meshes, and then we only have two nodes. So we'll label our ground node. Oh, it's already labeled for us. And so then we have V1. We'll call this V2. My pencil's running out of sharpness here. So as a shout out to Professor Marley, I'm going to bring in my Bojangles pencil. It's bow time. And so hopefully we'll get a little morale boost by solving using pencil with the snazzy logo on it. So with this then, nodal analysis has one drawback to it in that we get a lot of denominators. And we're going to have to factor out the lowest common denominator out of there and multiply times the greatest common factor. But that's an extra step. We want to make sure to do that, though, because it's a nightmare if you carry through all those denominators. But we plow ahead. What do? Okay, we're going to have three terms in the first equation. We're going to have three terms in the second equation. We write them through, we chug through the algebra, and we'll get our answers at the end. So for node 1, we get V1 minus 3 divided by 12. That's the current. That is actually the current I-12 that we're eventually going to look for, but we haven't solved for all of our voltages yet. And then we're going to get V1 divided by 6 plus 1. 1 is the current going out of that node, is equal to 0. Let's go ahead, multiply this by 12, and get a more sane equation here. So we're going to get V1 minus 3 plus 2V1 plus 12 equals 0. And then that will cook down to, 3V1 is equal to -9. And look at that. V2 didn't even come into play. So we do have two equations, and we do have two unknowns, but they're independent. So we could solve for that directly. And so we're going to just say that V1 is equal to -3. And so we've got that directly without having to solve any linear algebra. So for the second equation, we take a look at V2. We have one amp coming in, so we want to write these nodal equations as the current going out. We're going to have a -1 plus V2 over 10 minus 5 equals 0. We're going to multiply that by 10 to get rid of the denominator, so we're going to get -10 plus V2 minus 50 equals 0. And here we get V2 is equal to 60. All right, we've got our two voltages. That's not what the problem asked for, though. We were looking to find I-12. I-12 was this term right here. So it's going to be V1 minus 3 divided by 12. This term is what we're really looking for with I-12, but it's not too bad. When we solve for the quantity that's being asked for, then, we just say that I-12 is equal to V1 minus 3 over 12, and that is equal to minus 6 over 12, which is equal to minus 0.5 amps. And then in engineering notation, we would put that as minus 500 milliamps. Not too bad, but it involved a lot of steps and a lot of algebra. So solving for nodal analysis, we do end up getting the correct equation. We had to multiply by some of the greatest common factors and so forth, but not too bad at the end of the day. Now we get to our next problem, and we can see that it is identical to this first one. These two are identical, but now they ask us to solve it using mesh analysis. And they're very polite about that. So we need to solve this using mesh analysis. So let's move forward with that. If we were asked to solve this with mesh analysis, we might initially bristle. How many meshes are there? There's 3. Oh, great. 3 equations, 3 unknowns. I'm going to call it a day and go to an easy major like mechanical engineering. Well, let's plow ahead. So we've got these 3 meshes, and we were initially bristling, but wait a minute. Wait a minute. We've got current sources here. So the current I2 is the current that's going through the bottom. It's through the unshared portions. And we've got I2 directly. That's just going to be this current source here. And I3, oh yeah, I3, we've got a current source right here. So we've got the answer to I3 directly. Now the 5 amps is going in a different direction. But now we can say I2 is just going to be equal to 1. And I3 is just going to be equal to -5. Bonus. So we have these we have these currents directly by inspection. Now we only have to write one equation, and we'll have one unknown, but we'll have to substitute other variables in. Let's just write the equation as we'd have it. We're going to start at the bottom here. We're going to move around. We hit a minus sign, so we do -3, and this is going to be plus 12 times I1 plus, and 6 times, here we have I1 minus I2 equals 0. But look at this. We already know what I2 is. I2 is going to be equal to 1. And so this turns into a very easy equation here. We get -3 plus 18I1 minus 6 is equal to 0. And when we move these over, we get a 9 on this side. We get I1 is equal to 0.5. And that's a plus 0.5. So 0.5 amps, we can label it. All right, now we've got all of our mesh currents. Here's all our mesh currents. But they didn't ask us for the mesh currents. They actually asked us for I12. Well, wait a minute, I12 is going counterclockwise, I1 is going clockwise, and that I1 that we've solved for, we don't have to multiply, we don't have to divide, we just have to stick in a minus sign for the convention of the direction. And so I1 was found out to be 0.5 amps. I12 is just going to be minus 0.5 amps, which is equal to minus 500 milliamps. And that was what the question asked us for. And then when we go back to what we had solved before, we saw that we got minus 500 milliamps. We get that for both. And so we're confident of our answer. But when it turns down to it, I mean, you look at this and you say, well, that was pretty easy. And at the end, I didn't really have to do anything at all. So just because there were more meshes than there are nodes doesn't necessarily knock out mesh as a good candidate. However, you can solve it either way. Either way will work. You'll always get the right answer if you apply the formula and do the algebra. However, certain circumstances, one might be easier than the other. Thanks.